So as we look at the ventricles filling, again, this is going to be just that first part of this diagram up here. We're going to see very, very small pressure changes within the atria and the ventricles. So this is all going to again be based on the opening and closing of those valves to maintain those pressure differences. Pressure differences are important because this is how blood flow is going to occur from the top of the heart to the bottom of the heart and then out into the body. So as we see, the ventricular pressure is this black line and the atrial pressure is going to be this red line. As we see the ventricles filling, that the left atrial or the atrial pressure is going to be just slightly higher than the ventricular pressure. This is going to allow for these three phases to occur for that ventricular filling. Then as we come to that very, very quick isovolumetric contraction, meaning that the valves are closed and everything is just holding in steady very quickly, we're going to see this huge jump in ventricular pressure. Well, why do we have to have a huge jump in ventricular pressure? Well, one, we're going to see that these chambers, again, are as they start contracting, again, this is going to be that most powerful contraction. Therefore, we're going to see a higher amount of pressure at this point. But remember, the blood is going to flow out towards the body from the left ventricle, right? So the pressure in the heart is going to be the highest at the systolic contraction, or that systole of the left ventricle, because it now has to overcome the amount of pressure that's in the aorta. Because remember, blood is going to flow from a higher pressure to a lower pressure. So for the blood to flow out of the heart in the left ventricle, it now has to overcome this aortic pressure. So this large gap right here in pressure in the ventricles is going to be very, very important to allow that ventricular ejection to actually occur. Now, as you can see, as it continues to move on, and we have the AV valve opening again and the aortic valve closing, this pressure is now going to come back to where it was, and we're going to have that ventricular diastole. So, which is going to be consistent again with that T wave that is indicating that we are having ventricular repolarization. Now back to this ejection part, we're going to see that the ejection, or this big change in pressure, is going to be consistent with our QRS complex, mainly that R and S part, which is that depolarization of the ventricles, to allow that contraction to occur and allow this amount of pressure to increase. Okay, so from here, now let's go back to that first one real quick, just to go through as we are looking at the left ventricular pressure and to the left atrial pressure. We're going to find that as the blood flow is going from the atria to the ventricles, we know that because our P wave is right here, showing that we are going to have an atrial contraction here. As the AV valve then closes and blood flows into the ventricles, we're going to have that very large pressure change where systole of the left ventricle is going to occur. We have to have this large pressure change because it now has to overcome the amount of pressure in the aorta for the blood to flow outward. As the systole occurs, we can see that it is consistent with this ventricular depolarization. And then we can see as the aortic valve closes and the AV valve opens, we're going to see that there is a drastic decrease in pressure in the ventricles, and it's going to go where it's consistent with the atria as well. Okay, from here we're going to see that that is consistent with that T wave in our EKG that is going to depict that ventricular depolarization. Okay, so this is a really good graph in the sense that we can depict many different areas of what's happening in the heart at one time looking at one particular graph. Okay, so let's talk about how blood volume changes can affect the output of the heart. So if you can imagine the right ventricle, remember the blood flow from the right ventricle is going to go to the lungs. Well, what happens if the heart is pumping too much blood to the lungs that then the left ventricle can't maintain? Pulmonary edema is going to occur, meaning more fluid is going to stay in the lungs than has been pumped. Systemic edema is going to be where the left ventricle is pumping too much fluid or too much blood into the tissue of all the various portions of the body, which we'll talk about edema in the tissue a little bit more when we talk about vessels. But it's basically, we have to make sure that the amount of blood that's going out is consistent with the amount that's going in, and vice versa, or areas of edema can occur. This is where congestive heart failure is going to come into play. So when the ventricles cannot keep up with the amount of fluid that is being brought in, the ventricles are not pumping out the same amount of fluid. Therefore, it stays within the heart, and then it creates all different kinds of problems within the heart. So how do the circulatory system and nervous system interact with each other? So as we mentioned with the electrical conduction system, it is a fairly autorhythmic system, meaning that it does not need outside neural tissue or neural connection for it to beat. However, there are cardiac centers within the brain that are going to allow the modification of how the heart works. So there are going to be input from the sympathetic and parasympathetic systems. Remember, those are the fight or flights. So there has to be some kind of neural connection, because we know that when this fight or flight system has been activated, we know that the heart rate increases. We know that blood pressure increases. So it has effect on the heart in some sort of way, mainly from those catecholamines that are being released. So how is information actually given to the medulla? So if you remember in chapter 16, we had all different types of receptors that are going to sense different types of information that is going to be brought back to the brain. We talked about proprioceptors, which are going to be a change in physical activity or activity from the muscles and joints. So these are going to be the ones that are activated when someone begins to run a mile and the oxygen, it needs to be increased. So the blood flow needs to be increased. Therefore, the heart needs to pump faster. So these proprioceptors are going to be very important for that. Baroreceptors, we will talk about here as well as within the vessels. There are going to be certain areas within the cardiovascular system that are going to maintain pressure. So they're going to basically give input back to the brain saying that the blood pressure of this individual needs to be adjusted or it's okay. If it needs to be adjusted, it will actually act on the kidneys to potentially release some fluid so the volume of the blood stays constant. So baroreceptors are going to be found in the aorta as well as the carotid arteries, which we will talk about with vessels. Chemoreceptors are also going to be very important. These are going to detect pH changes. So blood gases, when we look at respiratory system, we're going to find are going to be very important to maintain the carbon dioxide and oxygen levels within the blood. So chemoreceptors are also going to be found within the vessels as well, mainly the aortic arch and the carotid as well. So as we look at heart rate, we're going to find that, remember, the normal is going to be, we say 75 beats per minute, but it can range between 64 to 75, and that's really going to be dependent on the individual. But with a higher resting heart rate, the individual has something called tachycardia, and anyone who has a lower resting heart rate has something called bradycardia. Now, bradycardia is something that is not as detrimental as tachycardia because certain athletes, remember we talked about people that are more conditioned and their heart beats maybe a little bit less, but they are still beating the same amount of blood volume because their body is just so much more conditioned. Whereas tachycardia can be an issue as we move forward. Again, remember the heart is going to beat a lot for your entire life. We don't want it to beat any faster than what it actually has to. So that's the problem with the tachycardia. Now, there are certain chemicals that are going to act upon cardiac tissue that are going to either raise the heart rate or decrease the heart rate. And those are called chronotropic agents. So if we want to raise the heart rate, those are positive chronotropic. Whereas if we want to decrease the heart rate, those are called negative chronotropic. Whereas inotropic are going to be agents are going to control how hard the heart beats or how hard the contraction of the heart is going to occur. Now, obviously, those are going to be more calcium agents or potassium agents that are going to affect how hard the contraction is going to be. Now, some chronotropic agents that affect the heart are going to be nicotine, thyroid hormone, caffeine, and potassium. Now, these are going to stimulate the heart rate or make the heart beat faster. Nicotine obviously is a stimulant. Caffeine is a stimulant. Thyroid hormone, remember, if we looked at how the mode of action for the thyroid hormone was all about the increase of metabolism. So these are positive chronotropic.